to do on the EAS in order to fix some. Yeah, I have seen while working on this several misbehavior with the EAS right now. I have listed some of them there, and the goal would be to fix all this misbehavior in the EAS, and taking advantage of that to change a bit the way the EAS is working so far. So here is a list that I have identified. Maybe there are more, but typically, so I will go then more in detail for each of them. But we often have some small tasks ending up on the big core, whereas there are some mid-core available. So we need to change things in the way the EAS is working on that. We have some tasks which are not optimally balanced and that are accumulated in one core. That's something I think has been done as well with the U clamp. The fact that we have some tasks which are misplaced because of the spare capacity. And then the other thing is that right now we are switching to the overutilize as soon as one task break the EAS or it doesn't fit anymore in the CPU. And that really break everything. I mean, especially in my case that I will describe. So the work queue can wake up periodically for a few microseconds, and that will make everything spreading over. And then you will spend the next dozen of milliseconds to pack everything back. And that's sometimes not even possible because you don't have any wake up scene. And the other part is the fact that with uClamp Max, with the system pressure, with the power budget and so on, we have more and more cases where the task is not wake up anymore. And EAS right now, it's only about I'm selecting the right CPU. But then if you stay on the CPU for hundreds of milliseconds, your decision might not be the right one anymore. So this is the typical, I have only used unitary tests because that was the easiest way to study the problem. But that's something I am facing with real use case. So here is a simple case. I have two tasks. One is a really short one that won't run fast. So I set the util min to 600. So this is a Dragon Board RB5 platform, just for those. So normally the utilization of 600 is enough to stay on the mid. So we have this typical case where the small task, the short task, is scheduled on CPU 7 instead of CPU 6 or CPU 4 or whatever. That should be the obvious choice. But that doesn't happen. And the main reason for that is that when the short tasks wake up, it needs to increase the frequency of the CPU and the group of CPU, but only while this task will run, which is quite short. Whereas right now, this cost of running at a higher frequency is applied for the whole duration. Meaning that in this case, for the medium task, the orange one, we will consider that for the full running time, it will run at higher frequency. So the energy impact is large. And in this case, the EAS decide to put this small task on the big core. Whereas in reality, what will happen is that the small task there will impact the cost or the energy. The impact will be really short for the other task. So, yeah.
I think that's the fact that we'll raise the frequency only while the bottom task is running. That's only possibly true if you have like rate limiting for frequency changes and things like that.
Yeah.
So
I agree, and also it's not only the running but the runnable part. To be honest, is as long as the task is in queue, we will apply this frequency boost. Right. But in any case, it's far shorter than what we are computing. But I agree. My point is really that it's just that the impact, instead of being applied only for a short part, is applied for the full period of the other task.
what about Vincent? What about the real implementation that they keep the frequency longer than is needed for a task? So the run queue actually remembers for 20 milliseconds the last frequency vote for higher frequency before going down. That's quite common in those governors.
Which governor is doing that?
Well, Scheduler has the filter up and down the same period. So,
No,
but on
not
Android
in
you
mainline.
have two.
In mainline, it's, I mean, right in this case, typically the frequency. So on a perfect system, the frequency will be increased when the task wake up and will go back to the previous when the task going back to sleep. But then we have some rate limit.
Yes.
But as far as I can tell, the rate limit is not 20 milliseconds. It can be 10. Okay.
It can be 10, but on the phones it can be going up. It's 1 millisecond, and going down they keep sometimes even to 20 milliseconds. There are two limits in those private governors clones of Scheduler.
We don't have these two parameters in the Scheduler right now.
Not in the
mainline. You're speaking about
yes, in the downstream.
Okay.
So yeah, it's unlikely to have actually per task VFS that fast. Like you will finish and you will go back to your previous frequency for the whole class.
I agree that just what I want to say is that right now the way we are computing, because even in the way EAS is computing that, we are not taking care about how long it will take to wake up the frequency, how long it will take to go back. It's just that in the way we are computing that right now, we said this OPP will be applied forever, which is not the case. And that's why we have this kind of situation where the small tasks end up all the time on the big, because the energy impact that is computed is huge, whereas in reality it will be shorter. I agree that this case it's the perfect way. And as you can see there, for example, you can see that we have a delay with the frequency. This is of the thing. But in any case, it's still better than that.
When we compute cost right now,
yeah,
I don't think we actually specify the time. It's just time is taken as one. So are we proposing introducing runtime into the calculation?
So my point is my point is that instead of right now we are summing all the utilization on all the CPU in the performance domain.
Yeah, we just sidestep the question of how long entirely right now.
My way of solving that is that instead of summing all this, because this new task will not impact on all, but only once it will be runnable. And in fact, there is two things. There is how it will impact the utilization, which is the block part, and how it impacts when it's runnable. And to make, when we are computing the utilization, we keep these two values, which is once I will be runnable, I will impact all the performance domain to this OPP. And you can compute that quite easily. But then we will go back to the other previous OPP. And usually, most of the time in such situation, the OPP is the same as before, which means that in the computation, that's even more easier in the sense that we just have to compute the impact while the task is runnable, because the OPP will remain the same otherwise. That's my point. And I don't know if it's there, but I can't. The goal is that's another thing that that's another point. But yeah, the point is that it's not only summing, I would say, blindly all the utilization and say that will apply for all the utilization, because it's not true.
Yeah, but so at your plot at CPU4, the frequency going down task, the schedule, as you can see, this is longer than just the running time of the task. Yeah. So this should be accounted actually.
Yes.
Not the task itself.
No, I agree. So the first thing is that it's not running but runnable, and then maybe we have to take into account some CPU fake latency time, something like that.
Yeah, the schedule.
And in this case, if it's 20 milliseconds, then we'll go to the full utilization at the end.
Mm-hmm.
But yeah, that's really something that happened quite easily, and I mean, the big core is bigger and bigger compared to the medium, so the impact is even huge, and there is also an impact from a wake-up latency point of view, because in this case, if you look there, this CPU is down, it's probably clustered R, really deep idle state. So it will take 1 or 2 milliseconds to wake up. Whereas the other one there are already, I mean, they are in a shallow C state. So that will help from a latency point of view, that will help from an energy point of view. But I agree that it's just that right now what we're doing is too coarse. We need to have a finer way to compute the energy.
Yeah, I agree.
So that's one of the first things. The other one is that right now we are using the spare capacity to select a CPU in a performance domain. But the spare capacity is not always the best choice, because it doesn't always reflect the running activity of the CPU. It includes this block utilization. And the other point is that when some CPU are saturated from utilization point of view, we can't make any difference. And when I was looking at that, what we really care about when we want to compute the energy impact, more than the spare capacity. So right now we have the assumption that larger spare capacity means a lower OPP. But you might end up with the same OPP with different spare capacity. And in this case, the impact on the power consumption will be the same, because the OPP that we will select will be the same. So instead of looking at the spare capacity, we are looking at the OPP and the cost for each CPU. And that will be used to select the CPU. And typically in this case there, so I just put 3 OPP, and that's it. It's just a simple thing. So we have 2 CPU0 and CPU1. So CPU0 is the one with the largest spare capacity. CPU1, because of block load, so this white things is the block utilization, and probably something just went back to sleep just before. So the utilization is still high, saying I was used recently. So its spare capacity is lower. But both CPU will use this. I mean, if you have the task, both CPU will use the same OPP. So we'll use the same cost. So the energy will be the same. So instead of just using the spare capacity, we are using the OPP and its cost to select the CPU. And when they're using the same cost, we can then use more input to select the right CPU, like the number of running tasks, like the average runnable things. It just helps us to select the one which is lightly loaded. Yeah.
Yes, it's just to give some insight for that heuristic of the spare capacity thing. I think you're right. There's a lot of cases where there are multiple CPUs which are not, which from the energy model perspective will end up with the same energy calculation at the end. The spare capacity thing is just it's a nice filter to just pre-select candidates that guarantee are going to be in the set of CPUs that will be the best.
Yeah.
The reason we did that is just because it's faster.
Yes, I agree. But the point is that it's not always true. In fact, behind the spare capacity, you are looking for the lowest OPP and the lowest cost. But in fact, with the with the lowest spare capacity, you might still end up with the same OPP and the same cost.
Yes, but it's just that by looking at the CPUs with by just selecting one CPU per cluster per performance domain, things are faster, and so you just need to pick one. And that's an easy way to do it. That's pretty fast.
My goal is to still do the same. I mean, at the end, you select one CPU per performance domain. It's just that right now we are looking if the CPU fit, if the task can fit on the CPU. If it's fit, we are looking for the spare capacity. In my case, is that if it's fit, I'm looking at the OPP that will be used.
Yeah, then you have to do OPP lookup. So it makes the search a little bit slower. It can be done.
Slower, so we will not have more loops, but instead of looking at the spare capacity, we are looking at the OPP utilization. So I agree that the computation is probably the first one is probably a bit more expensive, but the complexity remains the same. We will not look at CPU.
So I was going to add, we have made some experiments on some, and we look over all CPUs and trying to find maybe different CPU at some corner cases. And real world examples, well, the benchmarks that we have and workflows that we have, we couldn't see any benefit to change this kind of behavior of current EAS.
I don't want to look at all the CPU. I'm still looking at the same number of CPU. It's just that the way. Yeah.
The only problem you have is the blocked part of the utilization, right? At the moment you do the decision, that's the problem. You would like to put the task on CPU 1 rather than CPU 0 on your example.
Yes, in this example, but
Exactly.
that's the block, but that can be, I mean, that also happen without any blocking utilization as well. Because the OPP is a discrete thing. I mean, it's not if we have a infinite number of OPP, I would say the highest spare capacity will provide you the lowest OPP. But we have a discrete number of OPP, which means that for a range of utilization, you will use the same OPP. The energy will remain the same.
Well, yeah, and so we've been trying those experiments on some, to be honest. So we have 20, 25 OPPs per core, quite a lot, quite nice resolution. We couldn't find any other major improvements for the EAS because the normal workloads don't fit into these corner cases. And we were not there to add any complexity to the code if we can only see 1-2% of the improvement. And that was, we discussed this a few times with Bitma internally as well, to not put more complexity, which we cannot maintain just for 1%.
So to be honest, the complexity is not that much at the end. It's just that the input is no more spare capacity, but OPP cost. And that's it. And that just gives you another level, typically, that just gives you another level of decision there, like the number of running tasks, the previous CPU, and the average runnable. That's the point.
Just maybe the thing to clarify the part of that I don't understand. So in the example you have, so yes, putting on CPU 1 instead of CPU 0 is an alternative solution, but what's the benefit? Like, do you from the energy model perspective, CPU 1 is not better than CPU 0. So you're saying you want to have another deciding factor of breaking the tie between the two CPUs.
Yes. It's just that there, CPU 0 and CPU 1, right now, they give the same energy result.
Yes.
I agree. But right now, we not even consider CPU 1. We only consider CPU 0. And
but why would we? I mean, for now, right?
For now, that's the point. And the goal would be to take more input.
If you would have like utilization without blocking part, then you would choose CPU 1, even with the old approach of taking spare capacity.
Yes.
But you don't have. Okay.
No, and I could have put another one with only one big task, things like that. We were speaking about the things like that. Typically, the number of tasks running on the CPU is one factor of latency. I mean, so we can end up with a dozen of small tasks on the same CPU, and even if it takes only 1 millisecond per task, you will have to wait 12 milliseconds. On the other side, you can have, let's say, one big task, which means that even if we look at the slicings, you can preempt this one. You can run before the other one. That's the point. That's just another level. It's just that because the energy, at least the energy computed will be the same. I don't know, probably that will not be the same at the end, but the estimation will be the same. So then we can take more input, select an idle CPU, for example, because typically this one could be even idle. Right now, CPU 1, even if there is no CPU, we might not select CPU 1 because of this block utilization. Whereas this is clearly an obvious better choice.
So typically, I think what I personally envision as a better decision to break the tie between CPUs like that would be to take into account idle costs. That's really hard to do. So that's why we never did it. But this is like, if you want to break the tie, breaking it from trying to make the energy calculation more accurate to actually reflect the fact that you're right. I think CPU 0 and CPU 1 from the energy model perspective, they will get to the same energy value. In practice, they will not be.
Yeah.
So maybe that's where we could, that would be the deciding factor
Yeah.
for EAS in particular, because I think it fits maybe better in the intention. But I think you're right. There's definitely something there. We're just choosing CPU 0 because it's easy, and we just don't have any other information. But
my point is just that I think maybe it's time we can find a way to add more input to make some another level of decision. That's the point. The other one is that that's a well-known thing with uclamp max, so we can be misplaced. So the CPU are fully busy at a low compute capacity, and they are not overutilized because we have capped the max frequency. The point is that because the spare capacity is null in this case, I mean, we can't make any computation. That's another thing. In this case, the spare capacity is null in all the CPU. How do you make any difference at the end? And the only difference is making sure that you balance the task. And another thing that we are doing right now when we are computing the energy is that we are capping the utilization to the CPU capacity. But, so that's the example there. If you have two CPU, so either you have enough capacity and you increase the capacity. But if you're already at the maximum compute capacity, that's mainly meaning this additional utilization mainly means running longer. So we should not cap this. I mean, it's not because the sum of utilization is higher than the compute capacity of the CPU that we should cap that. It just means that we will run for a longer time. So the energy impact will be higher as well. That's another thing. It's quite obvious that helped quite a lot in this case.
I think this came clear when we introduced this one patch to allow to go into performance domain with max spare capacity equals 0, right?
Yeah.
This is related, and then we said there is still an issue, and I think this is what you described here.
Yeah. So that's really that. It's just that we have to stop capping that because obviously the utilization reflects the number of instructions that have been used by the CPU. So either you can make more, you can have more instructions per second, or you have to run longer. It's just that. So that's another thing that help quite a lot to spread all this. Because in this case, the impact when a task wake up. So yeah, that's another thing there. I mean, it's not always running task because you still need a wake up to make a decision there. That will be for the next slide. It's just that there, they still, I must put a small sleep time in order to wake up and make a better decision. So that just covers the case where we are waking. It's just an extreme case, I would say. And the other part is that what we are mentioning. So once, yeah, sorry.
I have a remark, but it's related more to the first point that you had with the uclamp min.
Yeah.
So you said that when you try to place a uclamp min task, you're going to more accurately compute the energy cost.
Yeah.
And you're going to do this because you're going to raise the frequency for a short amount of time, then go back to the previous frequency. Does it mean that if we use the uclamp definition that is right now, when we place a uclamp max task on such CPU, we are going to, for a short amount of time, lower the frequency to respect the uclamp max definition, and then raise the frequency back to the previous frequency?
So there will be probably there will be a frequency switch during the runnable time. And regarding the uclamp max, right now I think we are taking the max between uclamp min and uclamp max.
Okay.
So if you have a uclamp max there and a uclamp min there, you will boost the frequency for a short time to fit the requirement of this task, and then you will go back to the lower frequency. Yes.
Because I thought that for uclamp max, and if you set uclamp max for a task, it means that you don't want the CPU to run this fast. You want to limit the performance of the CPU when the task is running. So
So that's the aim to say, I don't need more than that to run. But then if you have a shared, I mean, then because you're sharing your CPU with other tasks, or even the OPP of your CPU with other CPU, you have to aggregate all the requests. And the final decision is usually the max of the mean. Okay. Something like that. So that's the point, yeah.
Okay. Thanks.
So the other point is there, 5 minutes, okay. So even when you have well placed all your tasks, also that the things there is that, let me describe. So I have some tasks which are, so I have 4 tasks with uclamp max, those one, which are on the mid-core. And then I have a task that is a small task and then start to be a long task before going back and becoming a small task again. So in this case, we have some misfit tasks that happen, and some CPU, the little CPU there, will become overutilized until we migrate the task. But because it's overutilized there, the load balance will start to happen, and the load balance will start to spread everything around. Or even if you have a work queue that you can have for a few dozen of microseconds, overutilized state that will break everything. So that break all the energy optimization that we did, and that break all the tasks are going up and down. I mean, the task stability is broken as well. So, and the other point is that we need some time to clear the overutilized state right now, because once the overutilized have been set, we have to go through all the CPU to make sure that there is no more overutilized CPU. So you have to wait for the next load balance at the system-wide level, which can be quite useful, especially when some CPU are already used. So the goal there would be, and we are skipping the find energy efficient CPU when we are overutilized, which might not be the right way to do in such a case. So the goal there is that even if we are overutilized, we are still using the find energy efficient CPU. And if we can make an energy efficient CPU with that, that's fine. Let's continue putting your task in this CPU. But if we can't because everything is overutilized, then we fall back to the default CPU. That helps to keep things more stabilized.
I think this CPU overutilization, we used to make sure that the energy calculation in find energy efficient CPU can work. And we don't end up in a situation where the utilization is bigger than the capacity or very close to it. So when we put another task on, it appears to be a very low cost, right? Because we are already saturated. With uclamp, it might not be necessary, or we have to maybe modernize this.
Yeah.
Okay.
That's the point. Yeah. So and this is what is happening for the same use case there. So you can see that even if we have some small things, all these remain the same, and we are minimizing. The goal is to minimize the overutilized spread of the task. I need to go there. Yeah, that's another thing. But the last thing is that with uclamp max and the fact that we are capping CPU, we have more and more cases where the tasks are not waking up anymore. And in this case, the frequency, find energy efficient CPU is not called anymore. So the task may remain stuck on the wrong CPU. I mean, you can have made a good decision 1 second before, which is no more the case now. And the system, in fact, is not, so the system is not overutilized, but we don't have any wake up to migrate tasks to a better CPU. And if there is an overutilized that happens shortly, it can just migrate one task on the wrong CPU and will get stuck in this situation for a long time.
Did you not also change the way misfit load balance can happen now also in EAS, right? But that's not what you're talking about.
No, that's the goal is to go even further in that direction. Right now, yes, we with the misfit task, we are skipping. We can do a periodic load balance for misfit tasks without breaking everything. But the goal would be to go further, not only on this misfit task, because it's not a misfit task in this case. The task fit on the CPU. It's just misplaced. So the goal would be to
okay, so sorry, this is because the UCLAM stuff, right?
Yes.
It fits, but it actually doesn't fit.
So it fits from a capacity point of view, but it doesn't fit for energy point of view. Maybe because, I mean, if you're stuck on a big core, you always fit on the big core. But maybe it's not the most energy efficient CPU to be used. That's the point. And you don't have any wake up anymore. So you must pull, a medium core must pull this task in this case. So you have to detect that you have such task on the big core and trigger the load balance only for doing this kind of I have mentioned that I think it's a misfit power task in this case. We have the misfit performance task that should migrate on the bigger core, but we can have the opposite case.
I have a question.
Yeah.
But if you consider uClamp max with some aggregation, so you add up normal utilization to uClamp max, then you shouldn't see this effect. So there will be wake ups for different tasks, not the one that you clamp maybe, but the other.
Yeah, but that's the point. I mean, you can have, because of uClamp max, you can have some tasks which are stuck on the big core. Because that's, I mean, when the tasks wake up at some point. It can be, the big core might be the most energy efficient one because all the other ones are used and you can run at a lower PP on the big core. So you start this task on the big core. Then the other CPU become idle, but because you will not wake up anymore, you will be an always running task.
With current uClamp max implementation, then it's aggregation with the current one mainline.
No, but whatever the uClamp max, if you don't have any wake up,
because you are running at too low frequency. But if you increase the frequency because you respect the other normal utilization, then you wake up.
Yeah, but why would you increase the frequency if you said I'm a task and I don't want to run more than half the max capacity?
I think Vincent is correct here. I think even some aggregation cannot solve the problem that you don't have any wake up time. So yeah, if we solve this problem, it benefits both sum and max aggregation.
So yeah.
Okay, so that was my question.
Whatever max, I mean, it's not a uClamp max policy at all. It's just that because we are capping the running frequency of the CPU, your task will not wake up anymore because usually it's a background task and it will run for a second and that's it. So, I mean, even if you are moving to the sum aggregated uClamp, you will have the same problem because you don't have any wake up. So it's not really a matter of, yes, max or sum or current task policy. It's really about waking up. So the goal is that to be able to detect this task and to use the load balance to pull that. So the case is not there, but that's something that is, you look at that as well, and we discuss on that. So and it seems that it's happening more and more often because we are capping more and more. We have more and more powerful smartphone, but we don't want to use this power all the time. So we are capping more and more, and we are in more and more cases where some tasks are not waking up that much, or even if it's 100, 200 milliseconds, that's still quite huge. Running 200 milliseconds on the big core, whereas you might run on the little, there is an energy impact there. Yeah, okay, and I think, yeah, that's it. Yeah, so these have been tested on the Dragon board. The next step is the Pixel 6 to have some real Android use case. And I need to finalize this load balancing before sending everything on LK now. And that's it.
Okay.
Probably come back 10 minutes, so that